Exercise 9. Hess law states that the overall enthalpy change for a cyclic process is 0. Why is this true? Because the pressure is constant, the volume is constant, delta H equal delta E, or because delta H is a state function, or none of these answers. I will draw a cycle. I will pass in transformation A from 1 to 2, then I will return from 2 to 1. From 1 to 2, the transformation has a value delta H. So from 2 to 1, the transformation has minus delta H. So in a cyclic process, the delta H total is equal to delta H minus delta H. So delta H is equal 0. And the answer is, since the enthalpy change is a state function. So the correct answer is D. MCQ 10. Which of the following reactions would be the delta H for the reaction be labeled delta H0 formation? In other words, which of these reactions is equivalent to the reaction of formation of the substances? And by definition, the enthalpy of formation of a substance is the energy exchanged. It may be positive or negative. It depends on the substance. So if the energy exchanged to form 1 mole of substances from its simple elements at the standard state. So we have 2 conditions. The first, we have to form 1 mole. And the second, from the elements at the standard state. So can we eliminate any answer? In all answers, we have formation of 1 mole AlOH3, 1 mole POCl3, 1 mole NO, 1 mole CaSO3. So we cannot eliminate directly one of these answers. Now we look to condition 2. What are the simple elements? AlOH3 is composed of Al, O, and hydrogen. The simplest element of Al is Al solid. That of oxygen, O2 gas, hydrogen, H2 gas. So the reaction 1, the reaction in A, is the formation of 1 mole of the substance from its simple elements at the standard state. So A is correct. B is incorrect, since PCl3 is a compound, is a molecule. This is not the simple element. So B is incorrect. C is incorrect because N2O is a compound, is not a simple element. D is incorrect also, since CaO and SO2 are compounds. The delta H for all these reactions would be labeled delta H0 formation. This is incorrect. So we have only one correct answer, which is A. Exercise 11. What is the enthalpy change of the third reaction in terms of the enthalpy change of the 2 given reactions? We have 2 given reactions. Reaction 1 has delta H1, reaction 2 has delta H2. We want to calculate delta H3 of the reaction 4 NH3 gas to 6 H2 gas plus 2 N2 gas. So this is method 1, which is the algebraic method, is to calculate delta H of a reaction from given delta H of reactions. So we have to make a combination in order a combination of the given reactions in order to obtain the global one. In the global, we have 4 ammonia. Look to the given reactions. In the second, we have 4 ammonia, and the ammonia is on the left. So we keep reaction 2 as it is. 4 ammonia gas plus 3 O2 gas gives 6 H2O gas plus 2 and 2. So in the global, we have 4 ammonia and we have appearance of N2. But we have O2 and H2O that should be eliminated. So we pass to other reactions. In reaction 1, we have H2O in the products. So we have to inverse the reaction 1 in order to put H2O liquid in the reactants. So if we inverse the direction of the reaction. So reverse the reaction 1, we obtain 2 H2O gas gives 2 H2 gas plus O2, but we need 6 H2O, so we have to multiply by 3. So reverse reaction 1 and multiply by 3. When you reverse, you change the sign of delta H, so minus. And when you multiply by a factor n, you have to multiply delta H by the same factor. So equal delta H for this reaction is equal minus 3 delta H1. Now we add the 2 reactions in order to prove or to see if we have the global one. We add the 2 reactions. 6 H2O liquid will eliminate 6 H2O liquid. 3 O2 gas is eliminated by 3 O2 gas in the product. So we obtain 4 NH3 gas gives 6 H2 gas plus 2 N2 gas. And this is the global reaction in the question. If our reaction is the global of the given reaction, so delta H of the global is the combination of delta H given. Therefore, delta H3 is equal delta H of the first plus delta H of the second, so equal delta H2 minus 3 delta H1. And the correct answer is D. To note that when we apply the algebraic method, the global reaction and the given reactions should be at the same conditions of temperature and the pressure. In this exercise, we don't have any indication that the temperature and the pressure of the 3 reactions are different, so we assume that these 3 reactions are at the same conditions of temperature and the pressure. Exercise 12. The value of delta E for the following reaction is minus 59.4 kilojoule per mole at temperature 298. What is the value of delta H at the same temperature? So we apply the relation, the relation of delta H and delta E for a chemical transformation. For a chemical reaction, the relation delta H and delta E is given by delta H delta E plus RT delta N. Pay attention. In the application of this relation, delta H and delta E used should be at the same temperature mentioned in the formula. If the temperature is 298, so you have to use delta H and delta E at 298 Kelvin. And this is our case. And delta N is the difference of the stoichiometries between the products and the reactants, and you consider only the gases. Delta N equal stoichiometry of the product. For carbon solid, we neglect the stoichiometry since it's not a gas, so is equal to 0 plus 3 minus 0, because C6H6 is liquid. So delta N is equal to 3. Therefore, delta H equal delta E plus 3 RT. Pay attention also for the conversion of the units. R is given in joules and delta E is in kilojoule. So if we want to use delta E in kilojoule, you have to transform R to kilojoule. Or you conserve R in joules and you transform delta E to joules. So delta E is minus 559.4 times 10 to the power 3 in joules plus 3 times 8.31 times temperature 298. So delta H equal minus 519704 joule or is equal minus 52 kilojoule per mole. I think we have error in this. Is minus 51974. So is equal minus 52 kilojoule per mole. And the correct answer is C. Exercise 13. At temperature T for iodine I2, the standard enthalpy of fusion is 16.1 kilojoule per mole and the standard enthalpy of vaporization is 45. Calculate the standard enthalpy of sublimation. First of all, we have to define what is the meaning of fusion, vaporization, and sublimation. All are physical transformations. The fusion is the transformation, is physical transformation with a change of state from solid to liquid, and the temperature of this transformation is constant. The vaporization is a physical transformation when we transform liquid to gas at constant given temperature, and the sublimation is the direct transformation, this is a physical, of a solid to gas at given temperature. So we have delta H of the fusion of iodine, I2, and delta H of vaporization. We have to calculate delta H of sublimation. First of all, translate the fusion to an equation, the vaporization to an equation, and the sublimation to an equation. Fusion process means I2 solid is transformed to I2 liquid, and delta H of this transformation is delta H fusion equals 16.1. This is a given value. Vaporization, so we transform I2 liquid to I2 gas, and delta H of this transformation is given delta H vaporization. Pay attention that the fusion and the vaporization occurs at constant given temperatures. So the sublimation, add these two reactions, I2 liquid will eliminate I2 liquid, so we obtain I2 solid to I2 gas. This is a sublimation from solid to gas. So since the sublimation reaction is the sum of the fusion and vaporization reactions, so delta H of sublimation is the sum of delta H of these two processes. So delta H sublimation equal delta H fusion plus delta H vaporization, and delta H equals 61.1 kilojoule per mole, and the correct answer is A. Exercise 14. Calculate the enthalpy of the equation C2H2 gas plus 5O2 gas that gives 2CO2 gas and H2O gas. This is the combustion of C2H2. given the bond energies in kilojoule per mole. Pay attention, he did not determine if the bond energies are bond energies. No, in this exercise, he determined that the bond energies are bond energies formation. In most exercises, he gives only bond energies and we have to deduce. Suppose this is not given formation, only bond energies. According to the data given, since the sign of the bond energies is negative, so this is a bond energy formation. We can apply the relation delta H of the reaction equal bond energies formation of the products minus bond energies formation of the reactants. But pay attention, to apply this relation, the reactants and the products should all be at the gas state, and this is our case. So the reactants and the products are at the gas state, so apply directly the relation delta H of the reaction is equal to bond energy formation in the products minus bond energy formation in the reactants. Now we have to determine the types of bonds in the reactants and in the products. So we have to draw Lewis structures. Lewis structure for C2H2 is HC triple bond CH, O2, O double bond O. For CO2, C double bond O, C double bond O, and for OH, for H2O, we have OHOH. I did not draw the lone pairs since I'm interested only in the types of bonding. So now we apply the relation. Delta H of the reaction is equal to 2 times delta H OH. We have 2 bonds OH, so 2 times delta H of the bond OH plus 2CO, 2 bond C double bond O times 2. So plus 4 delta H of the bond CO minus, we have 2 bonds CH and 1 bond CC and 5 over 2 bond OO. So delta H of the reaction, the bond energies formation are given in the table. We put their values and we obtain delta H of the reaction is equal minus 1230 kilojoule. So the correct answer is A. Exercise 15. Consider the following reaction. CH3OH liquid plus 3 over 2 O2 gas that gives CO2 gas and 2H2O gas, and delta H of the reaction is given. So he asked to calculate the formation energy of CO, so the bond energy formation of C double bond O, noted delta H0 CO. In some books, they use the term F, and I prefer to use directly delta H0 of the bond CO. So the trick in this exercise, the student will apply directly delta H of the reaction equal bond energies formation products minus bond energies formation reactants, and then to calculate delta H0 of CO. But we have trick in this exercise that the methanol given, CH3OH given, is at the liquid state. So we could not apply this relation directly. According to the data given, the sign is negative of the bond energies. So this is bond energy formation. Reactant and the products are not all at the gas state. Methanol is at the liquid state. So the relation of the bond energies difference cannot be applied directly. So what to do? In this type of exercise, we have a mixture of thermodynamic data. We don't have one type. So we don't have, for example, equations to apply only the algebraic method. We don't have bond energies formation to apply the relation delta H formation, delta H of the reaction equal delta H formation of products minus reactants. We could not apply the bond energies formation, which is method 3, since the reactants and the products are not all at the gas state. So we have to apply the method number 4, which is the cyclic method. Pay attention how to use or how to construct a cycle. The objective is to draw a cycle. So this is a closed triangle or a closed figure. Then from one direction to another, delta H is the sum of all other directions. This is the cycle method. So you have to construct a cycle, and the cycle should be closed. So, given the reaction CH3OH plus 3O2 gas to CO2 gas and 2H2O gas, and this is the delta H of the reaction given equal minus 613 kilojoule per mole. This is given. I will transform CH3OH liquid to CH3OH gas, and O2 is the same. So what is delta H of this transformation? Delta H of this transformation look like the transformation of methanol liquid to methanol gas. So this is a vaporization. So delta H of this transformation is delta H of the vaporization of methanol, which is given in the table 38 kilojoule per mole. Now I will close the cycle. So this is direction 1. This is the global direction. So this is direction 1. I have to close the cycle by direction 2. By this way. So this arrow is the sum of this transformation plus this transformation. Since we calculated delta H, and delta H is a state function that depends only on the initial state and the final state, I will call this delta H0 of the reaction. According to the principle of the initial state and the final state, I can write delta H reaction is equal delta H vaporization plus this delta H0. Look to the direction. This direction is the sum of the two other directions. And pay attention, the arrows should be in the same direction. So delta H0 is equal delta H0 of the reaction minus delta H0 vaporization. So delta H0 of the reaction equal minus 651 kilojoule. I calculated this delta H0. Look to this reaction. Are the reactants and the products all at the gas state? Yes. Gas, 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 gas. So in this reaction, I can apply delta H0 is equal delta H0 bond product minus the bonds in the reactants. So now we have to draw Lewis structures in order to know the types of bonds in this reaction. CH3OH, O2, O double bond O, CO2 and H2O. And pay attention, we have 2 H2O and 3 over 2 O2. Apply the relation of the bond energies formation on this reaction. I can say delta H0 of the reaction, which is calculated, pay attention, delta R H0, I means delta H of this reaction and not the delta H initial. This is the same notation, so write it delta H0 is equal bond energies formation product minus bond energies formation reactants equal. We have 2OH times 2 plus 2CO minus 3CH, 1CO and 1OH, and 3 minus 3 over 2 O double bond O. We have all data. Delta H0 is calculated by the cycle method, and we have all the bond energies formation of the bonds except CO, so we can deduce delta H0 of the bond C double bond O equal minus 803 kilojoule. So the correct answer is B. This is the cycle method. As a conclusion, think to construct a cycle when you could not use directly method 1 or method 2 or method 3, or in other words, when you have several types of thermodynamic data. Exercise 16. For copper, the variation with temperature of the heat capacity at constant pressure is given in joule mole minus 1 Kelvin minus 1 by the expression Cp equal function of the temperature. In this exercise, the Cp is temperature dependent. Calculate the change in the molar enthalpy of copper. So he wants to calculate delta H for this process. What is the definition of delta H? dH equal dQp when the pressure is constant. dH equal dQp. I have to put P, dQp equal NCp dt. So delta H is equal Qp equal integral of NCp dt from temperature T1 to T2. If Cp is temperature independent, so we obtain delta H equal NCp delta T. But in this problem, Cp is temperature dependent. So we have to replace the function of Cp in relation with the temperature, then to solve the integration. So delta H equal N from temperature initial is 293 to temperature final 323. Pay attention, T1 and T2 should be in Kelvin. In some exercises, the temperature are given in degrees Celsius. We have to transform to Kelvin. So in this exercise, the temperature are given in Kelvin times integral of 293, 323. We have to put Cp by its function of temperature equal 22.64 plus 0.0628 temperature dt. And now we solve each part separately. Delta H equal Qp equal integration 293, 323, 2264 dt plus integral 293, 323 of T dt. So it's equal 22.64 T between 293 and 323 plus 0.0628 T squared divided by 2 between 298 and 323. We put the temperatures by the values and we obtain delta H in joule. Why? Since when in this formula we write delta H as a function of Cp. So delta H has the same unit of Cp, and Cp is given in joule per mole per Kelvin. So we obtain the answer in joule, 737.2 joule per mole, and the correct answer is C.